All right, here's day 2 of intersection of lines. Um, so yesterday, at least to me, felt a bit scrambled. And I think that's because it's a lot of information all at once. We are looking at lines in two space, which is something that you've done grade 9, grade 10, looking at how they intersect. But we did it with a new notation, which is very different. And that's like intersection of lines is something that you've done every year since grade 10, solving systems of equations. It comes up in every course, comes up in advanced functions, comes up in calculus, but comes up sporadically to some extent. So it's not the freshest thing in our minds. And then doing it in a new notation, I think, is very different. So we did that, but then we also extended that to three space, and that's where we start to add on a lot of material for one day. And in three space, we add a new possibility. In fact, let me go back and let's talk about our four options. Okay, so in two space, we can cross at a point, we can be parallel and coincident or parallel and distinct. And those are each a different geometric interpretation or geometric situation, and then they each have a different number of solutions as well. And that's part of the classification of the whole process is what's the interpretation, but then also how many solutions does that mean it has. And then in three space, we add this fourth one where they are skew and it has no solutions like parallel and distinct, but it's not the same interpretation. So, for us, it's different. Regardless, we add this fourth that they're skew, and visualizing this is important. Understanding the difference just visually is important, but then also understanding how does that play out in the algebra? What does that look like as we are solving? That's the big part of what we're coming to terms with. So we're going to do, I think, 4 examples. There's 4 different outcomes, so you can guess at what will happen in our 4 different examples. But while we're doing it, it's more than just solving. It's also taking the opportunity in the different situations to look at different approaches you might take, different methods you could take, that sort of thing. So keep that in mind, that it's more than just getting straight to our answer, that at least in some cases, there are different paths you can take. And I know a lot of people want one path. They don't want options. Say, well, what's the best way? But all I can say is, you can pick a best way for yourself. That's fine. Uh, and I think we've talked about that. But expanding your mind to the options at least a little bit will help in some of the other areas. In some of the other systems that we're going to look at starting tomorrow and following that, it's not so simple that there's just one way to do it, that you really are going to be better off if you have a bigger understanding of what's happening. Okay, so we'll try to talk about that as we go, things like direction vectors, that sort of thing. All right, so let's take a look at this first one. For each system, this is the typical way the question will be asked, and it's 3 parts. Give a geometric interpretation, state the number of solutions, and solve the system where possible. Okay, so those are the 3 parts. The first thing I'm going to do, again, this might just be done by inspection. I might not actually write it out. That part will depend on what happens, or it'll depend on your habits. But you can certainly always write it out. It's minimal effort. And I will always write it out for the lesson because it shows my thinking. Okay, and I mean, if that's too much writing for you, and you think that's a waste of time, that's impressive because that's not a lot of writing. Anyway, you can do it by inspection. You don't have to write it out. So it's not necessarily part of the solution unless you get into this situation. Turns out this one's pretty straightforward. These direction vectors are the same. So, one is a scalar multiple of the other, and that scalar is 1. They just are equal to each other. But keep in mind, that if I could, like, one of them could be double the other, or it could be in the opposite direction, so multiplied by -5, or, you know, if they're any scalar multiple of each other, multiplied by 10, 100, a billion, whatever it is, that's good enough for us too. That's the same thing. Okay. And what does this tell us? This is the whole thing, is that if, like, we need to know, or we're better off, the quicker we know, the more ingrained into us it is what the relationship between the direction vectors tells us about the lines, or when we start adding planes, or all those things. Okay. Um, that's what we want to really get, is that, what does a scalar multiple mean? What does it mean about this situation, that sort of thing? Because in some cases, we might have direction vectors and there might be scalar multiples of each other, and that's irrelevant. That's actually not helpful. So it's not like it's just always a given. So again, it gets complicated the more layers we add on. But in this case, I just have two lines. Their direction vectors turn out to be exactly the same. And that tells us that the lines are parallel. Now, I think what some people might go to, oh, they're parallel, but the point's different. So they're parallel and distinct. Hold on, that's not how this notation works. Okay, there's no unique point that defines a line. The position vector to any point on a line will define that line. So it's just, if I started at the point that that position vector goes to, and I traveled along the direction vector however many times I want, if I eventually got to the other point or position, the point that the position vector goes to, then it would be the same line, right? Like, and if you didn't follow that, that's okay. But my point is, if you think of it, this is a vector, but if you think of it as a point, okay, it represents a point. And same thing with that. The fact that they're not the same does not tell us that these lines are distinct or anything like that. So what we have to do in this case is check a point on one line that's given, or I suppose if you somehow weren't given one, you just had to determine one, you would do that, but that doesn't tend to happen. So I'm checking that point from L1 in L2. Okay. And L2 is this. So I'm just rewriting this in parametric form. You don't necessarily have to. I know that as we add different possibilities of how we approach different questions, what some people get hung up on is, well, what work do I have to show? So you don't have to explicitly write out parametric form to use parametric form. When I start doing this, so I'm doing the x's, so I'm using this, x equals, and what is my x? It's that x in the point, right? So it's -2 equals -12 plus 5t. I can just go straight to that. I don't have to write it out in parametric form. But again, for a written lesson, if somebody's not watching the video, if they're just watching this, it maybe helps to know where things came from. So I like to write it out to be more descriptive. When in doubt, show more steps, but you don't have to. Okay, y is 3 equals 7 minus 2t, and the z1 is 7 equals 1 plus 3t. And what are we looking for? Just a consistent t. Okay, so I'm not this is not a system. This is 3 equations, each in one variable, each just t. So each of these can be solved individually for t. Again, that can be confusing because sometimes we get 3 of these and we solve it as a system, but that's when we have 2 variables, 2 unknowns, 2 parameters. Okay, and we don't have that in this case. So I am solving this. Adding 12 to both sides, I get 10 equals 5t, so t is 2. I get -4 equals -2t, so t is 2. So far, so good. And I get 6 equals 3t, so t is 2. And we're done. And that's our question. Like, that's our full solution. Now we just have to interpret it. And that interpretation is going to be huge. Okay. So over here, I'm going to say consistent t. Therefore, the point, -2, 3, 7, is on line 2. And that is not necessarily part of my solution that I have to write out, although I think it's a good idea to say that therefore the point's on the line. But what we definitely need to see is therefore L1 and L2 are parallel and coincident, and there are infinitely many solutions. Okay, so that is your final statement. This is true because the point was on the line, but when you get a consistent t, that means the point is on the line, so that also, means that we've determined our final answer. Okay, so in this case, I compared the direction vectors. That helped me to realize that the lines were parallel. And so I chose to check a point on one line, on the other line, the point that I know is on one line, check it in the other line. Obviously, don't check it in the same line. That's not going to help. Check it in the other line. And as long as you get a consistent t, that means that the point is on a line, which means they have to be the same line. Again, visualize that, right? Think about what that means. Think about what it means for the direction vectors to be parallel, and then a point on one line is on the other. What does that mean about direction vectors? We're talking three space here. I don't think I even mentioned that. I think all four of the equations or examples that we're going to look at are in three space. So we absolutely have to think about that, and it's going to be so helpful to visualize what that means in terms of the direction vectors and that sort of thing. All right, let's get into B. So again, I'm going to examine the direction vectors. And take a look, this one's in symmetric form. We don't see that a lot, but this is what we talked about when we introduced all this notation, is if you have to struggle to get the direction vector from symmetric form, well, then this whole question is going to fall apart, isn't it? So the direction vector comes from the denominators of the three parts. And the second direction vector is basically given. And what do we notice? We notice that, again, they are scalar multiples of each other. So -2 times d1 equals d2. Therefore, line 1 is parallel to line 2. Now, I can't remember if I mentioned this in the last one, but if this is the approach that you're doing, then this is a necessary part of your solution. So I said that you don't have to write out the direction vectors if they turns out that they're not scalar multiple and the lines are not parallel, then you don't have to show that work. You can just go straight into the next part of the solution, which obviously we're going to see in a different example. But if they are, and that's part of how you are narrowing down which of the four possible, in this case, four possible situations you're in, you got to show that. So you got to write out the direction vectors explicitly. What are they? And then state what the scalar multiple is and what that means. It means they're parallel. So all of this, everything I've written here is required for this solution. Okay. So again, I'm going to check point on one of the lines. Oh, and so how do we get a point from symmetric form? Symmetric form is x minus x, whoops, x naught over, we often call it m. Okay, so it's minus x naught, whereas x naught is the x coordinate of a position vector or point or whatever. Okay, so that means if it's x minus 2, it's positive 2. If it's y minus 3, it's positive 3. And if it's z plus 4, it's negative 4. There's my point. Okay. I could have used a point in the other one, sure. So I'm going to check that point in L2. L2 being, again, like I did last time, I'm going to write this out. And that's sort of for the lesson, but again, some people are looking for a straightforward step-by-step way that you can do this, and absolutely you can turn all of this into step-by-step, just saying step 1, compare the direction vectors. If this, then that, otherwise do this. Step 2, what's this? And step 2 might be write out the equation in parametric form. Like that might be part of how you turn this into a more step-by-step procedure. Three equals 1 plus 4t. Again, just subbing these into the parametric equations. And for z, negative 4 equals 5 minus 10t. So solving these, I get 0 equals negative 2t, so t is 0. Oops. I get 2 equals 4t, so t equals a half. Well, right there, we kind of know what's happening here. Negative 9 equals negative 10t, so t is apparently 9 over 10. I would solve all these, even if you get to 2 not being equal, I would solve all 3 because otherwise it looks incomplete. Okay, and again, what does this tell us? Inconsistent t means the point is not on the line. Okay, therefore, L1 and L2, now make sure that these are defined this way. They are given, I believe, as L1 and L2 in the question, but make sure that they are named appropriately. Sometimes they're not named with a number or whatever, right? So L1 and L2 are parallel and distinct. And that means there's no solution. So because there's no solution, I can't state what the solution is. That would be the third part of it. The geometric interpretation is L1 and L2 are parallel and distinct. Number of solutions is none. And so the third part we can't do. Similarly, up here, the geometric interpretation is they're parallel and coincident. So you have to say that whole part. You got to use the right words. Okay. And there are infinitely many solutions. What is the solution? In this case, we skip that because the solution is just both lines because it turns out they're the same line, but we're actually going to talk about this in a future lesson where even though we have infinitely many solutions, we have to state what the solution is. We can't just leave it at that, okay? So there's 2 examples. Those 2 are similar in that we were able to examine the direction vectors and stop there. Well, not stop there, but that gave us the information we were looking for, and we were able to just do a check to finish our solution, right? And we're going to obviously see in the next examples what happens when the direction vectors are not scalar multiple of each other. In fact, you can see that right away. That's what's going to happen in this one. What do we do in that case? And the solution will look fairly different in these cases, right? And so knowing the different possible ways that these questions can play out is going to definitely be a big part of all of this. All right, so let's get into this next one. You know, I'm going to start with the same thing, even though we've already done this by inspection. I would say in this case, especially when they're both in starting here in vector form, you wouldn't write this out. It would kind of be a waste of time, but I'm going to do it to show my thinking. And as always, you are more than welcome to do it if you're looking for a step-by-step process. And what we're noticing here is D1 is not equal to any constant times D2. They're not scalar multiple of each other. Therefore, line 1 is not parallel to line 2. Okay, so what do we do here? We consider the parametric equations and we set x's to x's, y's to y's to z's. Okay, so for the first one, I've got for my x, it would be x equals 10 minus s, and x equals 14 minus 2t. Okay, so that's my x, 10 minus s equals 14 minus 2t. Then I would get 2 minus 3s and negative 1 minus t for my y. So notice that I am not rewriting these out in parametric form first, because I'd just be rewriting it once and then writing it again. But you could, I guess, negative 5 plus 5s and negative 4 plus 3t. So negative 5 plus 5s equals negative 4 plus 3t. So now I have three equations, both in s and t, and this is a system. And again, what do? We choose two of them, solve the system, which means solving for s and t, and then check that in the third. So when I look at all three of these, I don't particularly see one that is going to be better than another. To me, these don't, there's none that are obvious. There was an example yesterday where we had some zeros, and so some of the parameters were gone, and so it was easy to solve for s or easy to solve for t. Of course, you're going to look for that, and if that happened in the third one, then I would use that. But I'm thinking there's nothing about one or the other that's better. In fact, this has a 5 and a 3, and that's going to be a little bit harder to work with. So I'm going to go with the x and the y. Okay, I'm going to choose x and y and just focus on those and ignore the z for now, and then bring the z back in at the end. All right. So I'm going to do, and there's I can imagine different teachers are going to do this different ways. When we get into the final stage of this unit, we're going to be solving a lot of systems, and I'm going to talk about a very particular way of solving those systems. And you could do these kind of like that as well. Like these will always kind of be in this form: constant and variable, constant and variable, constant and variable, constant and variable, right? Because they came from the parametric equations. So I could simplify this by getting constant, variable, variable equals constant, whatever it is, 2s plus t, or whatever it would be. I know that doesn't work out for this one, but equals some constant, right? Like I could work that out and put them all in that same form, but they're already kind of in the same form. So I'm not going to do any rearranging. I think that it'll be easy enough to use them in the form that they're in. So I'm going to do negative 3 times equation 1, and that is going to give me negative 30, positive 3s, and that's why I did this, minus 42 plus 6t, okay? And that way, when I bring equation 2 down, I get 2 minus 3s equals negative 1 minus t. And remember, I like adding. So that's why I did that. I'm going to be eliminating the s's because I'm going to add them. Okay, and I got negative 30 plus 2 is negative 28. And then I got 0s equals, looks like negative 43 plus 5t. And I end up bringing the 43 over. I get 15 equals 5t. So t is 3. And I'll call that equation 4. And I'm going to sub 4 into 1. And so I get 10 minus s equals 14 minus 2 times 3. So I get negative s equals, that looks like 14 minus 10 is 4, so 4 minus 6, which is negative 2, so s is positive 2. Okay. So I got S is 2, T is 3. Nice answer. Sometimes we get fractions and stuff, so that worked out nicely. Whole numbers, a little bit easier to work with. Check. Notice the similarities, but then also differences. And again, that's why this can be so complicated. I'm doing a check like I did in the other one, but the check that I'm doing is really different from the one that I did in the last two examples, right? So I'm checking this in 3. I solved 1 and 2, so I have to check in 3. You don't always check in 3. You check in whichever third one you didn't use to do the solving in the first case, okay? So this looks like -5 minus 5 times S, which is, sorry, plus, which is 5. And the right side is -4 plus 3 times t, which is 3, which is -4 plus 9, which is 5. Left side equals right side, which means basically consistent parameters, consistent S and T. So therefore, L1 and L2 cross at a point. There's one solution. And that solution is, and I think I said this the other day, you might want to do the solution first before doing your, before writing your final statement, because we want to write the whole final statement all together and just to organize our solution. But I'm going to use the t parameter. So t equals 3. And that means I'm subbing into L2. And I don't know that there's any particular reason why I did that. That's just what I chose to do. So x equals 14 minus 2 times 3, which is 8. Y equals -1 minus 3, which equals -4. And z equals -4 plus 3 times 3, which is 5. Which means our point is 8, -4, 5. Okay, and so the solution is, one solution is 8, -4, 5. Okay, so there you go. There's the one that has all 3 because it's got a solution. They cross at a point. There is one solution. The solution is, in this case, 8, -4, 5. You have to state all 3 of those things. Obviously, if we're saying the solution is that point, that means they cross at a point, but we want to see that statement as well. We want it to be summarized. Okay, one more, and then we're done, and we've seen one of each. Again, this is 3 space, so keeping all that in mind. All right, so my D1. Actually, you know what? This one looks wrong. So I think we already did this one. I moved a couple of examples around. Obviously, something mixed up. So that's okay. I'm just going to write it out. So we're not going to do this one. Okay. Get rid of that. And here's the example that we're going to do. L1 is in vector form x, y, z equals -2, 1, 0 plus t times 1, 3, 7. And L2 is going to be in symmetric form. Y minus 3 over 5 equals, sorry, x minus 3 over 5 equals y plus 3 over -5 equals 4 minus z over 2. Now, right away, one of the first things that we're going to see is that this part of symmetric form is a little wonky. So we want to fix that, okay? And so in symmetric form, it's x minus x naught over m1, y minus y naught over m2, z minus z naught over m3. So I would be turning this into negative z plus 4 over 2, which would be negative, factoring it out, z minus 4 over 2, or even better, z minus 4 over -2. That's actually the form that we want this to be in. Okay, that's going to give us our proper values. And this is a situation where maybe we in fact want to rewrite both of them in parametric form, just so we don't get ourselves confused. Um, this can be a great strategy if you start to get mixed up in, what's what, or wait a minute, which one came from which form or whatever. So that's 0 plus 7t, so that's just 7t. And then L2 is going to end up being x equals 3 plus 5. So I need to use a different parameter here. I can't use t. We're using s before. We often use m. I'm going to use m. Y is negative 3 minus 5m. And z is, from here, 4 minus 2m. And that's the part that's important. Why I had to rearrange all of that is because you have to get the right point z naught and the right coefficient for the direction vector. Otherwise, the whole thing's not going to work, right? So once in a while, there is going to be a little bit of extra work that has to happen to sort of make sure we have things in the right form, and just to analyze. Again, it just adds an extra layer of complexity, a little bit more difficulty. And so when everything's nice and friendly, we're all happy and we all know what to do, but then all of a sudden, there's just a tiny little tweak in the information that we're given, and that makes it that much harder, causes us to stumble a little bit, right? We all have experienced that. So now that I've written them out in parametric form, now I took the time to write them out nicely in parametric form. That's the form we like best. So now it's easy to go to my direction vectors. I don't have to write these out because they're not scalar multiple. So D1 is not a scalar multiple of D2. Therefore, L1 not parallel to L2. So I am going into the other type of solving that we did in the last example. And I've got parametric form, so x equals x, y equals y, z equals z. Okay, and I'm using parametric forms that I've already written out. So now this is going to be that much easier. Okay, got equations 1, 2, 3, and this is where we decide which two we're going to use, and then check it in the third. And I don't see any reason not to use 1 and 2, so I'm going to do the same thing and use 1 and 2. So I'm going to do negative 3 times equation 1, and that's going to give me 6 minus 3t equals negative 9 minus 15m. And then I'm going to just bring in equation 2. And the reason I'm doing that is because now I'm going to again line up the t's to be able to eliminate them. So that's 1 plus 3t equals negative 3 minus 5m. I'm going to add these. Okay. And I get 7 equals negative 12 minus 20m. Bring the negative 12 over. 19 equals negative 20m. M is negative 19 over 20. Yuck. That's okay. It's not going to be a big deal. Call that equation 4. Okay, and then sub 4 into equation 1 or 2, because we have to use, we started with those, we have to use those. Don't sub into equation 3 there. That's an easy mistake to make. Whoops. Oh, now I got to do it in the third. Not until you're all the way finished. You can't swap partway through. Okay, it has to, I chose 1 and 2 to start. I got to finish with 1 and 2, 100%. Plus 5 times negative 19 over 20. And using my calculator a little bit, this works out to 5 minus 19 over 4. Make sure we know that's a 19. And so t is 1 over 4. Okay. All right, so I got a value for m and a value for t, and I am going to check m equals negative 19 over 20 and t equals 1 over 4 in equation 3, because that's the one I haven't used yet. This is where I flip over and check in the other one, right? So 7 times a fourth, which is obviously 7 over 4, and the right side is 4 minus 2 times negative 19 over 20. Again, just using my calculator, I got to get a common denominator here, whoops, which you might not bother, but I'm going to choose to do that, whoops, 40 over 10 plus 19 over 10. Okay, just common denominator, just some fraction work, but you could plug that all into your calculator and not do it the long way. 59 over 10. What does that mean? Left side not equals right side. Therefore, L1 and L2 are skew. This is the fourth case. And there is no solution. And we're done because there's no solution, so we can't state the solution. So that's it. We did one of each of the 4 possible outcomes, one of each example, and notice the difference in all of them. Notice that in this case, the direction vectors were not parallel, so I had to set up the parametric equations, making them equal to each other, and do the whole solving a system, right? It's a fair bit more work. You got to think. Same within this case. And these were the 2 cases where they're not parallel. So there's 2 possible outcomes if they're not parallel. Might be skew or might cross at a point. And then here's one of the cases where they are parallel, the direction vectors, and the lines are parallel. And so this was less work, just checking a point in one of the other ones. I mean, we set it up in a similar way, but I would say it's a lot less work. We're not solving a system, just checking for consistent t. This one did not have a consistent t. This one did have a consistent t. So here's a great example in 3 space. And we saw parametric equations, we saw vector form of equations, and we saw even symmetric forms. So we saw all the different kinds of forms that we might see. Parametric form is going to be the straightforward one because that's the one we like to use for these anyway. Symmetric was the oddball there, but we saw that. So, this day has a little bit of everything for lines intersecting lines in 3 space. Okay, which is probably what we're more concerned with than in 2 space, but doing it in 2 space with the new notation is something that we've also done as well and that we need to know how to do. All right, so hopefully that's straightforward. I like this because you can compare the 4 different outcomes and see the amount of work and see the different approach and hopefully really see how looking at the direction vectors tells us a lot of worthwhile information, and it's worthwhile to do. And then tomorrow we're starting something new, and after that we're doing something new again. So we're adding on to this, and that always complicates things. And so remind ourselves that it is so important that we really, really understand what those things are telling us. I mean, we already saw with planes in the past, we're going to reintroduce planes and start working with them again, that direction vectors are not as useful, that we need to know the normal to a plane, okay? So we can't take for granted that everything comes down to direction vectors, okay? But there you go, there's an example of each, and it's a nice summary of intersection of lines in 3 space.